Hey y'all, welcome to our first lesson for social justice mathematics. We are going to talk about a living wage, um, which is a really cool primer into uh, what we do here in social justice mathematics, because it's kind of impressive how we can take math that we've known for quite a bit. Most of what you see here will be things you picked up in either middle or high school, uh, but just easy stuff like that is in the public consciousness can really be used to um, kind of describe and help us understand socioeconomic problems, and especially in this case, problems involving money. Everything from, as we see here, our taxes, the basics of money, and then some more complicated things, exponential growth and decay, which is more or less anytime you put money in a bank or into a savings account or into any sort of investment, you're going to be doing some sort of interest that is going to affect how that money changes. So if you ask yourself the question, how much money did you make at your last job, or you're currently working at your current job, you probably noticed that you answered in dollars per hour. All right, and this is an example of a rate of change that we use all the time in society, right? Miles per gallon is a thing we use in cars, as is miles per hour, right? Anytime we have blank per blank, we're talking about a rate of change. And so if we want to take that rate that we have for our job, so you make $20 an hour, and we wanted to convert it to just dollars, then all we need to do is multiply by the number of hours, and then boom, we've got the total number of dollars that we have in our bank account from whatever time frame we're looking at. So if we wanted to find earnings per week, pretty straightforward. How many hours did you work in that week? You just take your hourly wage, multiply it times the number of hours, and then you can think about this, if you want to think about it mathematically, as a fraction where you have hours in the denominator, hours in the top, right? If we're multiplying our rate times how long we worked, and those would cancel just like they would with numbers. So it would just leave us with dollars. So per year, same thing, right? You just have to figure out how many hours you worked in the year, and then you could go from there. And you could even, if you wanted to, break this down into smaller problems and scale it up, where you would talk about how much did you earn in each week? How many weeks did you work? Right. And we can break down that multiplication a little simpler than that rather than trying to figure out exactly how many hours we worked in a single year. Now, do we have enough information to do this? Yeah, definitely. Right. We have all sorts of things depending on your job, right? You can either check with your employer. Uh, I'm sure there's some sort of employee resource that they have. If you fill out a timesheet, there you go. That's already got it for you. Or if you work kind of a more steady job that is outside of something like, say, retail or food service, where you know you're working like a 9 to 5. Well, there you go. There's your hours for each day. So to convert this into something a little more mathematical, because this will help us later, we want to take the English that we're using to describe how much we get paid, and we want to convert it into math. So generally when we do this, an easy way is change the word is for an equal sign, and then figure out how to balance both sides of that. So in this case, we have two things that we do not know in this sentence, right? 7.25 an hour for how many hours is a total of how many dollars, right? So what we're going to do is we're just going to pick two symbols to represent those blanks in our mathematical sentence, right? So we have blanks in our English sentence. We're going to pick two variables to represent it mathematically. Usually we use letters just because they're easy to write. If you want to pick smiley faces or hearts, that is all you. So we'll let T be our total time in hours, and then we'll let P equal the total pay. And then what we would have is our pay is 7.25, right? How much we make an hour times how many hours we worked. So we have two different variables living here. One is called the independent variable T, and one is called the dependent variable, and that was P in this case. And so the idea here is one is the thing we're inputting, one is the thing we're getting out of our equation. So we're inputting the number of hours we worked, and then this equation is telling us how much pay we get. And the pay we get depends on the number of hours we work, hence dependent variable and independent variable. So what we can do is represent this equation, right, this mathematical sentence with a graph, a line that gives us essentially every possible outcome for plugging in however many hours, right? So we can, one, quickly determine if we work so many hours, what the pay is. And then also we can notice trends here, which of course we're on an easy example. So the more hours you work, the more pay you should get. But for more complex examples, we want to make sure we can visualize that trend a little easier. So what is the least amount of information we need to find a line? And we can do two things here, really. Either 2 points, right? If I take any 2 points, I can draw a line between them, and that is a unique line, right? There's no other line like that. It's not like I can fit multiple lines to that. Or I can pick a point and a direction, right? So if I know where to start and I know where to go from there, that's enough as well. So if we have, say, a 0.43 and a slope of -3.4. That's kind of like our starting point and our direction. So what I would do is I would plot down that point, and then from there I would go -3, remember rise over run. So we're going to rise -3. So go down -3 and then run 4. That gives me my next point. And then I connect up the two and that gives me my line. And I only have to find those 2 points. Once I find those two, I'm good to go. So I can go the other way if I'd like, or you can go backwards. So instead of rising -3, you could rise +3 and then run -4 to the other side. And that will work as well. That'll give you different points. So let's see if we can put this into action here and try and understand what's going on. So here is a very relevant example, right? This was a few years ago. Congresswoman Alexandria Ocasio-Cortez, or AOC as she's commonly referred to, suggested having a marginal tax rate of 70% on income over 10 million. So regardless of your feelings on this, right, what we want to do is use the mathematics we have to give us all the information we need to make a decision. Right? The mathematics itself is not going to make the decision for us, but we want to be as informed as possible when we make this decision. So most people, when they approach this, did not investigate further, made up their mind based on whatever factors they felt were necessary, and the meaning ended up getting warped quite a bit. So let's look at what this means, right? From a historical context, just to briefly mention, right, the marginal tax rate was a high in the Eisenhower administration of 91%, and then was reduced to 70% under Kennedy and Johnson before subsequently being reduced further. So this is a proposal to go back up to 70. But how exactly is that marginal tax rate calculated? So what happens with American income tax is there are different brackets. And income within each bracket is taxed at a different rate. So let's take a really easy example here, right? Let's say there's only 2 tax brackets, right? You get taxed 35% on incomes 10 million and under, and then anything over that 10 million, it goes up to 70%. So it would double from 35% to 70%. So how much does somebody whose income is $10,000 pay in taxes? Well, if you look at it, right, 10,000 is less than 10 million. So we would do 35% of 10,000 to get our total taxes. Here's another cool thing. When we have the sentence that we're reading, we see of in there. So 35% of $10,000. We can just treat that like multiplication. So what I would do is 0.35 here times our $10,000. So we would pay $3,500 in taxes. Now, what about 10 million? Right. Well, if we look at our tax bracket here, right, it says 35% on incomes 10 million and under. So that's including 10 million. So even at 10 million, we're still paying 35%. So we do the same thing, 0.35 times our $10 million, right? And then that comes out to 3,500,000. Okay, cool. Now here's the kicker, right? This is where everybody gets mixed up. $10,001,001, right? All of a sudden that puts us in our second tax bracket. Now we've made over $10 million. So we're going to be taxed at 70%. It's not how that works, right? So the way our marginal taxes actually work is all the income up to, in this case, $10 million is taxed at 35%. Only the stuff we make past $10 million gets taxed at 70%. So what I would do here is I would break it into two stages. The first $10 million I make, I would pay 35% taxes on that. So that would be our 3,500,000 that we talked about before. And now that extra dollar that I made over, that's the only thing that gets taxed at 70%. So 70% of $1, right, would be 70 cents. So I would end up paying $3,500,000.70 for making that extra dollar. That extra dollar doesn't mean that everything else gets taxed at 70%. It's only the stuff that we make past that $10 million. Now we can represent this with a graph just like we talked about before, but we have to be a little careful about this because we have different scenarios, right? We have under $10 million or equaling $10 million, or we have over $10 million. And so what we want to do here is use what we call a piecewise function, which is basically just a function we make of pieces. Yeah, the name's not clever, I know. So here for $10,000, 0.35 times 10,000, that gives us our output. If the input is $12 million, right? Okay, so we have our first 10 million, that's taxed at the 35% mark. So that's this piece here. But now we have another piece. Everything past that has to be taxed at 70%. So here's our 70%. And then we have our 2 million here, which is the stuff we made over $10 million. So the first one, 3,500,000, just like we mentioned before. And then everything over that $10 million, that gets taxed at 70%. So that is 1,400,000 if we do this piece here. Add the two pieces together, and that gives us our total taxes just shy of 5 million. So we can generalize this a little bit if we use the variables like we talked about before. When we are dealing with under 10,000, or not 10,000, sorry, $10 million, right? For X, we have 0.35 times X, X being how much we made, right? The output here is our total amount of tax we have to pay. So that's going to be capital T there. Now, if we make over $10 million, well, then we definitely made at least $10 million, right? So we're going to do 0.35 times that first $10 million we made. And then we're going to look at the leftover. And the easy way to find the leftover here is just to take the total amount we earned and then get rid of that first 10 million. So X minus 10 million, that'll tell us how much is left over. And that's the stuff that gets taxed at 70%. So we do 0.70 times that leftover bit, right? And once we add those together, just like we did up here, that'll give us our total amount of taxes. So same as before with the function, but this time because there are different options based on how much money you made, we have to use a piecewise function here. Now we can simplify that out if we just do a little algebra. So you'll notice this one stayed the same. This one, we just combine some like terms and we end up with this. And so this is our simplified version of that formula, right? We would plug in X, how much money we made, and then we would get output T, the total amount of taxes they have to pay under this marginal tax system. And you can graph both of these, right? The way we graph these is anything before or including 10 million falls under this first case. So we would graph out this line. This is 0.35x and graph it all the way up here. And then once we hit that 10 million, then it changes, right? So now we're under our new line here, 0.70x minus 3.5 million. And so when we do that, it changes here. So you can see how our taxes change as we're increasing. And then once we hit that 10 million, right, it doesn't shoot up drastically because our whole thing is not being taxed at 70%. It's just the leftovers. So it goes up a little steeper, but not too much steeper. And you can see the two examples we did here, right, for 10 million and 12 million with both their input and their output. Fun fact, when we're talking about this 10 million, right, that is less than 0.005% of all US households. That's a little dated. That's from a few years ago, but it has not shifted that much since then. So this is not a problem that most people are encountering. Now, in 2018, this was the tax bracket here. So you can see we have a couple different things. If you make $0 up to 13,600, that is 10%, right, of your income gets taxed. Next tax bracket, we go up from 13,601 to 51,800, and now it shifts to 12%. And you can see they've actually kind of done the work here for us in this tax bracket, right? They said 1,360 plus the amount over this. That's because of the same stuff we did earlier. So the first bit we made here gets taxed at 10%. So if we made $20,000, we definitely made at least 13,600. So that bit gets taxed, and then we look at the amount over that and tax that at 12%. And you can see it's the same process here, just different numbers. It goes up 22, 24, 32, 35, finally up to 37, right? So this is a piecewise function, right? So we have our pieces here that tell us, just like we had before, this would be on the right-hand side, right? Our total income is less than 13,600. Our total income is between 13,601 and 5180, right? And then we have our rule here that tells us how we get that output. So each piece of that is a line. Now, when it comes to other things, right? So savings in particular, lines kind of go out the window, right? What we have when we deal with things like savings accounts is usually some sort of exponential growth. So we'll have an amount of money that we're able to invest. We'll use P to represent that. It stands for principal, so the amount you start with, right? And then let's say your bank offers a free savings account at a rate of R%, right? So what will happen is, assuming everything is compounded continuously, right? There are some exceptions to this, but they aren't that different in the long run. So we put this amount P into our savings account. It's gaining interest at this R% rate. And then we can calculate the amount that we're going to earn after so many years by using this formula. So the easy way I remember this is just PERT. I just say PERT, and it's P E to the RT. Now, E is not our variable here, right? We only have principal, rate, and time that we talked about. E is actually Euler's number, which is a number where the rate of change of the function e to the x, the exponential function, is also e to the x. So basically, it's the number where everything works nice. We'll leave the rest of that until calculus to discover exactly what we mean by that. But for now, just know that it's the number that makes everything work nice. Your calculator will have a button that says E, or if you just type in Euler's number or E number into Google, it will tell you exactly what it is. It's kind of like pi. It's one of those not terminating decimals. So you'll probably get a super long decimal answer there, but usually your calculator will have a button for that. So when we look at an example of this savings, right, let's say we have a family that's able to save 10,000 over 1 year, put into a savings account earning 2% interest. We would take all that information, we would plug it in. And so over 5 years, we would get the following. So we have our principal here. That's how much we start with, right? So that number goes here. 2% interest. So we convert that to a decimal. So 0.02, that lives up here, right? PERT, P-E-R-T. So our R goes here, and then our T goes over here. So 5 years. So we do that. Boom, there's the amount of money in the account. So you'll notice we still have that $10,000 from before, but we've gotten an extra $1,051.71 just from the exponential growth there. So let's say we have a second family that, instead of starting with 10,000, starts with 1,500, right? And they get the same interest rates, the same kind of account, right? We would do the same thing, right? 5 years, 2% interest. The only thing that's changed here is our principal. So we have 1,500 here instead of 10,000. And then the rest of it stays the same. and we end up with $1,657.76. So you can see we have the original 1,500 we started with. That's in here as well. And then we got an extra $157 and some change out of that. So we'll talk a little bit later about the conclusions that we can draw from this. And by we, I mean you, when we do our worksheets. They have some fun discussion questions, but I want you to just think about these two scenarios and some things you notice between them. So another thing to think about here, right, is how many families do we think can save $10,000 in a year, right? Or another way to phrase this question is, how long do you think it would take you or your family to save $10,000? Right, so these are some things we want to talk about in the future. Now, as fun as compound interest can be when we're saving money, it can also be a double-edged sword when we have to borrow money. So you'll notice, right, when you take out a loan, it will also have an interest rate, and this goes for everything from a loan payment for buying a house to the loan you take out when you buy a car, if you take a personal loan for anything, a business loan for anything, or something a little more, we'll call it predatory, like a payday loan. So let's run through a scenario here. Your car just broke down and the repairs are going to cost $300, right? If you don't have your car, you can't drive to work, and you'll lose your job because you need to be at your job to do your work. You've been able to save $115, but it's not quite enough. There is a place nearby that will give you a loan, right? For any amount less than $500, you just have to pay $25 up front, right? And then they will provide a 2-week loan, and the interest rate is 400%, right? So these numbers actually come from a few years ago, 2018, 2019, about that. But I will tell you, if it's changed, it's only changed for the worse. So we can use the same equation here to get back the total you have to pay in the 2-week time frame. Now, one thing to point out here is we had to pay $25 up front. So we needed 300. We started with 115. We had to pay $25. That puts us at $90 now. So I have to borrow $210. All right, so that's my principal going into this. That's how much I'm borrowing. That's how much I start with. So 210. My interest rate is 400%. So convert that to a decimal, and it's just 4.00. So that goes here, right? And then we have to deal with the 2-week time frame. Now, 2 weeks is not the same as years, which is how we talked about it here. And so we need to convert weeks to years. Well, how many weeks in a year? There's 52. So we can do 2 over 52, and we can put it in there. So 2 weeks you can think of as 2 over 52 years, or 2 52nds of a year, right? Which is not a way most people normally think about it. But in terms of our formula, that's the units we want to have here. So we do that. I will do an example later where I actually crunch these numbers to show you how it works, and we can get our final answer. And then you will do an example where you crunch the numbers. But for now, I will just let you know that you will come up a little short after this. And so you've been able to gather $40 over these 2 weeks, right? But our loan place, they got to be paid in full. The good news for somebody, maybe not us, is that they will give you another loan, right? But since they issued you a loan already, they're going to raise the interest rate to 450% to cover the difference. So we can calculate how much we owe at the end of this next 2 weeks as well, right? We got to crunch some numbers here. So we were able to pay off 40 of it. We had to pay 25, right, to get our actual loan again. So now we're left with just $15, right? And we have to pay back 210 from up here. And so we have to borrow another, I think, $195 on top of that, pay off our first loan. So don't worry, you don't have to follow along in your head. I will write all this stuff out so you can see exactly how I go about this. But I just wanted to walk you through it just for a minute. Okay, well, that finishes up our first lesson. So You do have your worksheet, right? That is going to be due the day of the first test. You will turn that in on Canvas. And then also, right, something to think about, right, to kind of approach this from more of the social justice aspect as opposed to just the mathematical aspect, right? It's worth it to reflect on how people are being paid, right? How much money are people getting for different jobs, right? Are there jobs you think are underpaid? Are there jobs you think are overpaid, right? And if you had all of the answers, or at least all of the power, right? How would you reframe the way we pay people in order to make it, in your eyes, more fair? So I'll see y'all in the next one, and thanks for watching.